Hello. Today I'll be giving my presentation on cross-domain few-shot learning for videos. For our motivation, few-shot video action recognition typically needs large labeled in-domain source datasets. However, novel classes can belong to different data domains with different characteristics. The cross-domain few-shot learning problem for videos has been previously unexplored, with existing benchmarks having class overlap between the source and target datasets. Not only can we not have this class overlap, but cross-domain video datasets can also have drastically different spatiotemporal dynamics. In this paper, we propose cross-domain few-shot video action recognition. Our method leverages self-supervised learning and curriculum learning. We use self-supervised learning to learn generic representations and curriculum learning to balance the information from the source and target domains. We also introduce an evaluation protocol for this problem in the video setting. Our task is 5-way 5-shot classification of the target dataset. Previous work for images uses MIDI ImageNet as the source, and target datasets like crop disease, Eurosat, ISIC, and ChestX. For our problem, we use kinetics as our source dataset, and challenging target datasets that have unique characteristics like unique actions that you wouldn't normally see, and fine-grained video classification tasks. For our method, we start with pre-training a video MAE on the unlabeled source and target data. We follow this up with curriculum learning using the labeled source data and the unlabeled target data. Our student and teacher models are initialized using step 1, and the student is trained on the source and target data, while the teacher is updated as a moving average of the student parameters. Finally, we replace the student classifier and fine-tune it on a labeled support set for evaluation. Here, we see our self-supervised pre-training stage, where we use the unlabeled source and target data. We follow this up with curriculum learning, where it has 2 parts. Our supervised loss, which is the student classifier on the labeled source data, and a consistency loss, where we take a weakly augmented set with its unlabeled target data and pass it through the teacher and sharpen it for pseudo-labels. And this is used to score the strongly augmented target data passed through the student for the final consistency loss. These 2 losses are combined for our final loss in this stage, and we use lambda to scale the consistency loss. It starts out very low in the beginning, so that we mainly focus on supervised loss on the labeled source data, but as training continues, it increases so that we focus more on the consistency loss and the target dataset later in training. Finally, we have few-shot adaptation, where a new classifier is learned on the student using the labeled target support set and used for evaluation. Here, we show our main results in the paper using Kinetics 400 as our source dataset. We use UCF 101, something v2, HMDB 51, Diving 48, and RareAct as our target datasets. Here, we compare our method to 2 cross-domain few-shot learning methods for images and 2 video few-shot methods. As you can see, our average result is a 4% improvement over the previous highest benchmark. We also show our results using UCF 101 as the source dataset instead, and have a similar improvement, as well as use Kinetics 100 as the source dataset. And again, we have an improvement over the previous benchmarks. For our ablations, we look at the effect of removing different components of our proposed model using Kinetics 100 as our source dataset. Here, we use equal loss weighting to show what happens when we keep lambda as 1 throughout the experiment. We have no temperature sharpening, where we use the teacher logits directly as pseudo-labels for the student. And we also have self-supervised training and supervised training as 2 benchmarks where we just go straight from pre-training to few-shot adaptation with no curriculum learning at all. And we can see across all of our data sets how much each of these components contributes to our final result. We also look at the effect of varying the source dataset size and the effect on its performance on our model. Here we can see as we start from Kinetics 100, go to 200 and all the way up to Kinetics 400, we can see that increasing the source dataset size directly improves our model's performance. Here we also look at different varying shots for our few-shot classification and look at our results with only 1 shot for few-shot evaluation, as well as 20 shots in our next slide here. And as you can see, we still show improvement over the previous benchmarks in each of these 2 cases. That is all that I have. Thank you.